In the previous lecture on model fitting with ASCR, we talked about building capture histories by hand. In this lecture, we will dive a bit deeper into fitting models and learn more about the data objects we need for this, how to import or create these, and use these data objects for our purposes. Towards the end of the lecture from chapter 2 on abundance estimation, we had a look at some R code already with which we fitted a model to our detections from this example shown in the top right. This is the same code. So we already know that we can use the fit.ascr function to fit an SCR model in R. We'll now have a look at the three objects that this function requires at bare minimum as inputs. These are the capture history, the traps, and the mask. So we'll start with the detectors and then speak about capture history and the mask. And I chose this order as information from the detectors flows into the capture history and the mask. Let's start with the detectors. So we need information on the coordinates of the detector locations. So we need to have the coordinates using a Cartesian coordinate system. So for example, we have the coordinates for detector 1 as these, for detector 2 as these, and for detector 3 as these, and so on. Notice that the units here are meters, and of course this is a theoretical example, but you could use, for example, the UTM coordinate system when you analyze your data. In the R package ASCR, the detectors are usually referred to as traps. We'll now just have a quick look at the object D2, which contains the required information for the detectors. It's important that these are in the correct order. So if the ID of a detector is 1, and you refer to this detector as detector 1 in the captures object, which we'll talk about later, the information for this detector must be in row 1 here. So we see, using the head function, that the information contained in the object, in the D2 object, has 2 columns. And these are just the spatial coordinates of each of the detectors, the X and Y coordinates, which we saw in the previous slide, where the units are in meters. This is an important point actually. Functions in the ASCR package automatically assume that these coordinates are given in meters and will automatically do all the conversions necessary to calculate the density estimates in hectares. These units are coded into the functions. Now on to capture histories. We have already learned how to build capture histories ourselves in the previous lecture. Turns out that you don't have to build your capture history yourself. You can use a function from the ASCR package to do that for you. And we'll use this function in the next slide, but you will need to organize your capture data in order to make use of this function. Let's have a look what I mean with capture data. So here's the capture data from this example. This is shown as a screenshot of the Excel CSV file, which contains the data. It only shows the first 20 odd rows here, but there were more rows that are not showing here. There are 4 columns in this data sheet: session, ID, occasion, and detector. Some of these may seem odd to you at first, like session and occasion, and you wonder why we need them. And my answer to that is not to worry about why and what so much at this point. But we need to include them as the ASCR functions will look for this specific information. So they're mandatory and need to be included. We'll start with the ones that might make most sense. So ID refers to the individual animal identifiers, the unique IDs that we gave each animal we detected. The fourth column, so the fourth variable, is the detector, which is the ID for the detector and needs to match the order in your object, which holds the detector locations. By the way, the rows here in the capture data refer to the individual detections. Each time a detection is made, a new row is entered. For example, G1 was detected by detectors 1 and 2. So we have 2 rows for G1. Animal G2 was detected by only one detector, detector 2, so only one row for G2, and so on. So the captures data has the individual detections as the individual records. Each time a detector made a detection of an animal, there's a new record in this object, and the number of records per animal depends on how many detectors they were detected by. This is in contrast to the capture history, where each animal was a record. Here in the captures data, there are no extra records about a detector not detecting an animal. You don't need to fill in the information that detectors 3 to 16 did not detect animal G1. The other two variables, session and occasion, refer to the temporal pattern of the sampling, and we talk about these later. But just for brief, session, we only have one sampling session in this example, so we just fill in ones for each record. And the variable occasion refers to the sampling occasion. We only had one, so all records are 1. In the next slide, we'll have a look at how we can import these data into R. So we start importing the Excel file with the captures data into our R workspace. The function read.csv brings the data into R. All we need to do is tell it where to find the data. I have the file captures.csv in a folder called data, and captures.csv is the file name. And then we have to give the object a name. I call it captures. That's the name that R will contain the captures data in. The structure function, str, will give you an idea what the structure is of a particular object. The object we want to have a look at is captures. This is a data frame with 101 observations of 4 variables. You might wonder why 101 observations when we had 71 detected animals. Well, this is because we had multiple detections of several animals, and here each record represents one of these detections. So this data object has the same records and variables as the CV file we just looked at. Nothing has changed, except now this is a data frame in the R workspace, and we can work with it here. We see from the output of the structure function that there are 4 variables in the captures object: session, ID, occasion, and detector. Same as in the CSV file. So this function, the structure function, does not change anything in the dataset. It just gives us a nice idea about what the data object is and what it contains. We can also have a look at the data in the object using the function head. This will print the first 6 rows of the object. This looks a bit more familiar to see it in this format because it looks similar to the CSV sheet from the previous slide. And in the next slide, we'll use an ASCR function to create a capture history from these data. So we're going to use the function create.capt for these purposes, which requires 2 objects as inputs: the captures data and the object containing the spatial information on the traps, called D2. And when we look at the object that this function created, we can see that it contains the object bin capped, which is equivalent to our capture history from before, with the 71 animals as the records and 16 detectors as the columns, and ones and zeros representing whether the detector detected the animal or not. As a side note, it is important to use the function create.capt to create your capture history as opposed to building it yourself. This will ensure that the object has exactly the right structure for model fitting for all the functions we're going to use in relation to model fitting. And because these functions will look for specific information in specific places. For example, have a look at the lighter gray line. I grayed it out to make it a bit easier on the eye for you, but it is there and it might be frightening to look at. What does all this mean? Attributes, dim names. Well, the reality is we don't have to worry about these things. They need to be there, but using create.capt takes care of that everything is in good order and everything is in the right place for the next steps. So next to the mask is simply a grid of points throughout the study area from which an animal can be detected. These points are shown in the map, which also shows the detector locations, the big black dots, and the boundary of my study area, the black box. You might wonder, why are there so many points outside the black box? And this is an important point to remember. Animals could be detected from outside the study area, so I've included grid points here outside the black box. You might wonder now how you might get this mask. Well, luckily there is an ASCR function that creates this for us. Let's have a look at it. So we use the function from the ASCR package create.mask to create the mask, which requires two inputs. The object D2 containing the information for our detectors and the value for a buffer. This value indicates a distance at which we believe that we could not be able to detect animals anymore. The units for the buffer are again in meters. In this example, we use 1000 meters as the buffer. It is important to set this large enough so that no animals that were further away than the buffer could be detected by any detector. Remember, in a real example, we do not know where the animals are or how far they are. We only know if they were detected or not. So this requires a bit of prior knowledge about your animals when deciding how large of a value to choose. You could argue that you could simply set this to an extremely large value, but this means that you will have an extremely large number of grid points, which will slow down the calculations immensely later on when fitting the model. Having a look at the object shows us that it's similar to the D2 object, so the mask is simply a data frame with two columns containing the spatial coordinates for each grid point. In order to give you a better idea what this mask object is, we can plot it by using, the plot function. And we can plot the detectors on top of the mask to see where they are in relation to it. So from the plot, you can see that the mask only includes points at 1000 meters maximum distance from any of the detectors, hence the rounded corners. Here we go. So let's have a look and summarize the required steps for model fitting. So we need to organize our detector coordinates into a traps object, like D2 from our example. We can use the function create.capt to convert our capture data into a capture history. And lastly, we need to use the straps object to create a mask, which we can do with the function create.mask. These three objects are required at minimum to fit the SCR model using fit.ascr. We have one additional key point to take away from this lecture. Capture histories along with the detector locations and mask are used as inputs for fitting models in ASCR.